Hello and welcome to day 2 of induction. Today we're going to talk about induction proofs using divisibility. So you'll notice that the problems that you have for this set are going to be about something like, in this case, 5 divides n to the 5th minus n, or other problems like that with divisibility. So get yourself ready for notes, and we're going to get started. I'm not going to relist out all the steps of induction, but I'll make sure that I'm labeling them next to the proof. So we're going to start with, in this case, our first step. So prove that if n is an integer, where n is greater than or equal to 0, then 5 divides n to the 5th minus n. So in this case, we're going to start with our smallest number, which in this case is, say, that n is equal to 0. So that's our smallest one, and then we'll build consecutively because we're talking about integers, just like you would with natural numbers. So that's why we talked about base case is usually 1, but occasionally it will be something different. So say n is equal to 0. Then what we can say is that what we want to show is that n to the 5th minus n is equal to 5x for x in the integers. So this is the question, is this true? Well, we've got 0 to the 5th minus 0, which is equal to 0, is equal to 5 times 0. 0 is an element of the integers, so that's just fine. Now, as I said before, I'm not going to end up writing out the entire assumption statement because I don't want the video to be too long, but what we can say is that we know that 5 divides k to the 5th minus k for some k in the integers. And what we are going to want to show now is that 5 divides k plus 1 to the 5th minus k plus 1. Now, just as before, in our algebraic proof, we're going to start with the statement we know. So we can say, we know 5 divides k to the 5th minus k. So what that means is that k to the 5th minus k is equal to 5x for some x in the integers. Right? This is the definition of divisibility. Now, what's important here is this is going to be a slightly different step, is I want us to think about k plus 1 to the 5th minus k plus 1. Because what we want to end up doing is manipulating our equations to get this expression. Now, this expression is a complicated expansion, and so I want to know exactly what it looks like, and that's going to be really helpful for my proofs. So I'm going to start by using the binomial theorem to expand k plus 1 to the 5th, which is k to the 5th plus 5k to the 4th plus 10k to the 3rd plus 10k squared plus 5k plus 1. So that's the entire expansion. And then we have minus k minus 1. We can do a little simplification here and here. We can also then, and I'm not going to, what some of you might think to do is, oh, well, we can simplify here and we can simplify here. And there's a reason I'm not doing that. And that's because this term and this term together are what we know about. So the way I'm going to rewrite this is I'm going to say that k to the 5th minus k, put those together, and then the other terms, you can think of these as the terms that aren't in our original expression that we know is divisible by 5. Are in another set. So we know k to the 5th minus 5k, k to the 5th minus k plus this expression is equal to here. So if I'm thinking about what we know, this is what I end up wanting to add to both sides. So then I can say, well, k to the 5th minus k plus 5k to the fourth plus 10k cubed, and I am writing small because I want to fit a lot of things here on both sides, equals 5x, I'm going to scoot this over a little bit farther even, because what this is this equation up here. So I've got this, I added this term, and I have to add it to both sides. So plus 5k to the fourth plus 10k to the third plus 10k squared plus 5k. So I add the same thing to both sides. Now what we've just shown is that this whole expression is k plus 1 to the fifth minus k plus 1. Right? That was the point of this solving. And on the other side, we can say that this is then 5, and I can factor out a 5 from both, x from the first term, plus k to the fourth, plus 2k cubed, plus 2k squared, plus k. Now, x plus k to the fourth, plus 2k cubed, plus 2k squared, plus k, we can say that's equal to an integer by closure because this is all multiplication and addition. So what that means is then k plus 1 to the fifth minus k plus 1 is equal to 5y. Therefore, we can say that 5 divides k plus 1 to the fifth minus k plus 1, which is what we wanted to show for consecutive numbers. Finally, you can state your conclusion here at the end that if we have true for 0 and true for consecutive numbers, then 5 divides n to the fifth minus n for all integers greater than or equal to 0. Again, let me know if you have any questions. You can set up a Zoom call, shoot me an email, or leave me something in the comments.